Welcome to the Curious Voyager. It's good to have you here tonight. Wherever you are, curled under a blanket with the lamp still glowing soft in the corner, or lying flat in the dark with your eyes already half closed, or somewhere on a late train with the window cool against your cheek, you've found your way here. And that's enough. You don't have to do anything now. You don't have to follow every word. You don't have to remember a single thing by morning. Just let the sound of it settle around you like a warm quilt being drawn up to your chin. Before we begin, and I'll keep this gentle, if you enjoy these slow late-night journeys and you'd like a few more of them waiting for you, a quiet like or a subscribe genuinely helps this small, sleepy little channel keep going. Small creators like me really do lean on it, and if you're already here with us, already subscribed, thank you. Truly, it means more than you know. So tell me, before your eyes get too heavy, where in the world are you listening from tonight? What time is it in your corner of the dark? I always like to imagine the little constellation of us, scattered across the world, all drifting off to the same strange story. And it is a strange story tonight, one of the strangest I've ever tried to tell you softly. So here's my usual promise and my usual little warning. I'll do my very best not to make this so interesting that it keeps you awake, but if it does, if somewhere in the middle of it you find your mind wide open and wandering, well, at least you'll have learnt something beautiful. A fair trade, I think. We'll move slowly. We'll take it one small mystery at a time, no rushing, no cramming, nothing you have to hold on to. If you drift off before the end, that's perfectly all right. The atoms will still be here when you wake. The whole strange story will still be waiting, patient as ever, exactly where you left it. So settle in. Let your shoulders drop. Let the pillow take the full weight of your head. And let me tell you about a little cloud of atoms somewhere in a laboratory in Munich that broke one of the oldest rules you think you know. Imagine, for a moment, a tiny huddle of atoms. Not many. Around 100,000 of them, which sounds like a great many, but on the scale of atoms is almost nothing at all. A faint whisper of matter, a puff so small you could never see it, never feel it, never hold it in your hand. These particular atoms are a kind called potassium-39. Potassium, the same soft silvery metal that lives, in trace amounts, in a banana, in your own blood, in the salt of the sea. And these 100,000 potassium atoms have been cooled. Not cooled the way your tea cools on the nightstand, not cooled the way a winter window fogs and chills, cooled far, far beyond anything the ordinary world has words for, chilled down to a billionth of a degree above absolute zero, a nanokelvin, 1,000 millionth of a single degree above the coldest that anything is ever, in principle, allowed to be. Sit with that for just a breath. A billionth of a degree. The coldest natural place we know of in the entire universe, a distant, ghostly cloud of gas called the Boomerang Nebula, drifting some 5,000 light-years away, a place so cold it is colder than the faint afterglow of the Big Bang itself. Even that unimaginable place sits at about 1 degree above absolute zero. And these little lab-made atoms in Munich are 1 billion times colder than that. They are, by any ordinary reckoning, among the very coldest things that have ever existed anywhere. The coldest-looking, most fragile, most delicate little cloud you could ever imagine. And here is where the story tips over into something that shouldn't be possible. Because those same atoms, that coldest-looking wisp of matter, that billionth of a degree breath of potassium, were, at the very same moment, hotter than the core of the sun, hotter than lava, hotter than a lightning strike, hotter than anything with an ordinary temperature anywhere in the cosmos. Not a little hotter, not somewhat hotter, hotter than it is possible to be, in the ordinary sense, hotter than infinitely hot. I know how that lands. Read it aloud to a friend and they'll tell you you've made a mistake, or that I've misspoken, or that it's just a silly play on words. The coldest thing ever made, and also the hottest thing that can exist, at the very same time. It sounds like nonsense. It sounds like I've mixed up two sentences. And I promise you, gently, that I haven't. This is real. It was published, carefully and soberly, in one of the most respected journals in all of science. And by the time we've drifted through the whole of it together, slowly, softly, no rushing, it will stop sounding like a trick. It will start sounding, I hope, like one of the most beautiful and quietly reasonable things the universe has ever let us glimpse. But before we go any further, let me set one thing gently to rest. Because the story, when it first reached the world, came wrapped in a phrase that has confused almost everyone who's ever heard it. People said these atoms had been cooled below absolute zero. Below zero. As though the scientists had found some secret basement beneath the coldest cold, some hidden step down past the bottom of the stairs. And that mental picture, I want you to let it go, softly, right now, before it takes root. Because it's the single most common misunderstanding about this whole business, and it points you in exactly the wrong direction. Nothing here is colder than absolute zero. Absolute zero is still the floor. It's still unreachable, still the coldest that anything can ever get, and nothing in this story ever goes beneath it. That old law stands, untouched, exactly where it always was. The strangeness isn't that these atoms went below the bottom. The strangeness is that they went off the top, that they reached the hottest state there is, not by climbing down past zero, but by climbing up, and up, and up, past infinity itself, and coming out somewhere on the other side. We'll get there. We'll walk that path together, one careful step at a time. But hold on to this much for now. Like a night light left on, negative temperature does not mean colder. It means hotter. Hotter than hot. Hotter than the very hottest you thought there could be. Now you're probably feeling the first little tug of that question, the one that always comes. How can that possibly be true? And I think the honest answer, the answer that dissolves the whole paradox, the way a sugar cube dissolves in warm water if you just leave it be, starts somewhere you wouldn't expect. It starts by admitting that almost everything you were ever taught about what temperature actually is was, well, a little white lie. A useful lie. A lie your teachers told you because the truth was harder and you were young. But a lie all the same. Here's the lie. You were told, most likely, that temperature is how fast things are moving. That heat is motion. That a hot cup of cocoa is hot because its little molecules are jiggling and dashing about at great speed, and a cold glass of water is cold because its molecules are sluggish, slow, barely stirring. And for most of everyday life, that picture works beautifully. It really does. Warm things do have faster moving molecules than cold things, most of the time. In the ordinary world of stoves and ice cubes and summer afternoons, it's a good rule of thumb, it gets you through the day. But it isn't what temperature really is. It's a shadow of what temperature really is. The shape you see on the wall, not the thing casting it. And to understand tonight's strange little cloud of atoms, we have to turn around, slowly, and look at the thing itself. So let me tell you what temperature actually is. And I'll go gently, because it's a subtler idea than fast means hot, and it deserves a little room to breathe. Temperature, in the deepest and truest sense the physicists use, is not about speed at all. It's about a relationship between two other things, between energy and something called entropy. And I know entropy is one of those words that sounds like it belongs in a dusty textbook, so let me hand you a friendlier version of it. Entropy is roughly a measure of how many different ways a thing can arrange itself while still looking, from the outside, like the same thing. It's a count of possibilities. A count of the little hidden configurations a system could be in. Picture a child's bedroom. If the room is perfectly tidy, every toy in its box, every book squared on the shelf, there's really only one way for it to be tidy like that. One arrangement. Low entropy. But if the room is messy, oh, the ways it could be messy are almost endless. The blocks scattered here, or there, or by the door, the socks under the bed, or on the lamp, or draped over the chair. 1,000 different messes all count as messy. Many arrangements. High entropy. Messiness has more ways to happen than tidiness does, and that, in the gentlest possible terms, is what entropy is counting. The number of ways. Now, temperature, real temperature. Here is the true definition, and I'll say it plainly and then soften it. Temperature tells you how much a system's entropy changes when you feed it a little more energy. That's it. That's the whole heart of it. If you pour a small spoonful of energy into a thing, and its entropy, its number of possible arrangements, goes up a great deal in response, then that thing is cold. And if you pour in the same small spoonful of energy, and its entropy barely budges, hardly climbs at all, then that thing is hot. Let me say that again, differently. Because it's the hinge the whole night turns on, and I want it to settle in soft and sure. Temperature is the slope. Imagine a gentle hillside where the horizontal direction is how much energy a thing has, and the vertical direction is how much entropy it has, how many ways it can arrange itself. As you walk to the right, adding energy, the ground rises, because more energy usually means more ways to be. And temperature is simply how steep that hill is at the spot where you're standing. The physicists write it as a tidy little relation. 1/T equals the change in entropy divided by the change in energy. 1 over the temperature is the steepness of the entropy versus energy hill. That's the real thing. That's the thing casting the shadow. And notice, softly, no need to strain, notice what this means. A cold thing is a place where the hill is steep. Add a little energy and the entropy leaps up. Because a cold thing is hungry for possibilities, gaining lots of new arrangements for every scrap of energy you give it. A hot thing is a place where the hill has gone almost flat. Add a little energy and the entropy barely rises. Because a hot thing is already sprawling across nearly all the arrangements it can reach, there aren't many new ones left to unlock. The steepness fades as things heat up. The hill levels off. Hot means flat. Cold means steep. That's temperature, seen for what it truly is. Now, why does the old lie, the hot means fast lie, work so well most of the time? Because for the everyday stuff of the world, the two pictures agree. When you heat a pot of water, you're feeding it energy, and that energy really does make the molecules move faster, and it also opens up more and more ways for all those molecules to be arranged and share the energy around. Faster and more arrangements go hand in hand out here in the ordinary world. So the shadow lines up neatly with the thing, and you never notice the difference. You could live your whole warm and comfortable life and never once need to know that temperature was secretly about entropy's slope and not about speed. But tonight we've wandered somewhere the ordinary world doesn't reach. And out here, at a billionth of a degree, in a cage of laser light, the two pictures come apart. And when they come apart, it's the true one, the slope, the entropy, the hill, that tells us what's really going on. The old lie about speed just shrugs and falls silent. It has nothing to say about a place like this. So let's stay with the true picture a little longer, because there's a feature of it, a very ordinary seeming feature, that turns out to be the secret door. For all the everyday matter you've ever touched, the water, the air, the metal of a spoon, the stone of a wall, there is a simple, reliable fact. When you add energy, entropy always goes up. Always feed energy to normal stuff, and the number of ways it can arrange itself always increases, never decreases. The hill only ever climbs to the right, it never turns and heads downhill. And because temperature is the steepness of that ever-climbing hill, and the hill always climbs upward, the steepness is always a positive number. The temperature is always positive, always some value above absolute zero. That's just how ordinary matter behaves. Give it more energy, it finds more ways to be, its entropy rises, and its temperature stays a good, ordinary, positive number. And why does the hill always climb for normal stuff? Here's the gentle reason. Think about the energy of a molecule zipping around in a gas. How much energy can it have? Well, as much as you like. Really, there's no ceiling on it. A molecule can move a little faster, and a little faster still, and faster again, without limit. There's always another rung higher up the ladder of speed, and because there's always more room above, always more higher, faster states for the energy to spread into, feeding in energy always opens up new possibilities, new arrangements, more entropy. The ladder has no top, so the climbing never has to stop. The hill goes up and up forever. Hold on to that image, softly, as you drift, the ladder with no top. The energy that can always go a little higher. Because that, precisely that, is the thing our little cloud of potassium atoms was missing. Somebody, in a lab in Munich, found a way to put a lid on the ladder. To build a room where the energy could not keep climbing forever, where there was a highest rung, a ceiling, a maximum beyond which nothing could go. And once there's a ceiling on the energy, the whole story changes. Once there's a top to the ladder, the hill of entropy can do something it can never do in the ordinary world. It can rise, and then near the very top it can turn and come back down. And when the hill of entropy turns and heads downhill, when adding more energy starts to decrease the number of ways a thing can be, instead of increasing it, the slope flips. The steepness becomes negative, and the temperature, which is nothing but that steepness in disguise, becomes negative too. Not colder than cold negative, off the top of the scale negative. The hottest place there is. But I'm getting ahead of us, and I promised we'd go slowly. We'll build that ceiling together, carefully, in a little while, the cage of laser light, the clever trick with the atom's own stickiness, the whole delicate machinery of it. There's no rush at all. Let's just rest, for a moment, in what we've already gathered, and let it sink in soft and deep. We've learned that temperature was never really about how fast things move. That was the shadow, the useful lie. Temperature is really about entropy, about how the number of a thing's possible arrangements responds when you feed it a little energy. Steep hill, cold, flat hill, hot, and for all the ordinary matter in the world, the hill only ever climbs, because the ladder of energy has no top, so the temperature stays forever positive, forever an honest number above zero. And we've learned that the whole secret, the whole impossible-sounding heart of tonight's story hides in that one word. Ceiling, cap, a top to the ladder. Take away the endless room above, Put a lid on how much energy the atoms can hold, and you make it possible for the hill of entropy to crest and fall. And a falling hill of entropy is a negative slope. And a negative slope is a negative temperature, and a negative temperature, strange as it still sounds, is not a colder cold. It's the far side of hot. You don't have to hold all of that. Let it wash over you and through you. The pieces will still be here. If you're feeling your eyes grow heavy right about now, let them. This is exactly the sort of thing that's lovely to fall asleep inside of, a warm, strange idea, turning slowly in the dark like a mobile above a crib. There's nowhere to be, nothing to finish. Just the quiet unfolding of one gentle mystery. Let me linger a little longer on that flattening hill, though, because I don't want to leave you with only the words. I want you to feel it. Think again of that tidy child's room and the messy one. When the room is very tidy, very cold, in our little picture, very low in energy, almost any small change makes it messier. Nudge one toy out of place, and you've moved from the single tidy arrangement toward the vast ocean of messy ones. So near the tidy end, a little disturbance buys you a lot of new possibility, a lot of new entropy for a little push. That's a steep hill. That's cold. But now imagine the room is already thoroughly, gloriously messy, every possible mess more or less achieved. Now nudge another toy. Does it get much messier? Not really. It was already about as messy as it could be. There simply aren't many new kinds of mess left to discover. So near the messy end, a disturbance buys you almost no new possibility. The hill has gone flat. And flat, remember, is hot. Now here's the thing that only happens when there's a ceiling. In an ordinary room, you can always make more mess, because there's always more space, more energy, more room on the floor. But imagine a room so strictly bounded, so tightly capped, that there's a highest possible state of messiness, an absolute maximum of disorder, beyond which the room physically cannot go. And then imagine you keep feeding it energy anyway. What happens once you're past the messiest point? Something wonderful and backwards. Past the peak of maximum mess, adding energy starts forcing the room toward a new kind of order. A strange, high-energy order. Every toy flung up onto the highest shelf, every sock pinned to the ceiling, an arrangement that takes a great deal of energy to hold, and which, precisely because it's so extreme and so specific, has fewer ways of happening than the broad muddle in the middle. So as you pour in still more energy, the number of possible arrangements starts to shrink. The entropy falls, the hill turns downhill, and your temperature slips over the edge, past infinity, and lands on the far hot side of everything. That, in the softest possible terms, is what those 100,000 potassium atoms were doing in Munich. They'd been pushed past the peak, most of them shoved up onto the highest rungs of a ladder that for once had a top. And in that inverted, top-heavy, strange, high-energy order, their entropy had begun to fall as their energy rose, and so, by the true and honest definition of the word, their temperature had gone negative. Which is to say, their temperature had gone hotter than hot, hotter than infinite, hotter than anything you could point to in the whole positive numbered universe. Isn't that a lovely, impossible thing to carry toward sleep? That hotter than infinity isn't a poet's exaggeration, but a careful, measurable, published fact. That it lives, right now, in the ordering of the temperatures themselves, an ordering we'll trace together, slowly, in a little while, all the way up through the positive numbers, up to infinity, and then around and over the top to the negative side, where the very hottest state of all quietly waits. For now, just breathe. Let the room around you be warm and dim and safe. There's a hillside somewhere in the dark, a hill made of entropy, and for everything you've ever known it only ever climbed. And tonight, in one small, impossible corner of the world, someone found a way to build a fence at the top and coax the hill to crest and turn, and in that turning made the coldest-looking thing that has ever existed into the hottest thing there is. We've only just stepped onto the path. There's so much gentle strangeness still ahead, the ceiling made of light, the atoms taught to pull instead of push, an old crystal flipped in 1951, and a secret hiding inside every laser you've ever held. But all of that keeps, all of that waits. For now, wherever you are, whatever the hour reads in your quiet corner of the night, let's just rest here a moment longer, on the true meaning of a word you thought you understood, and let the hill of entropy rise and fall, slowly, softly, behind your closing eyes. Let me sit with you a while in that gentle place, before we go on, because I think it's worth turning this one true idea over a few more times, the way you'd turn a smooth stone in your palm in the dark. There's a reason the physicists prefer their quiet definition, the slope of the hill, to the friendly old lie about speed. And it isn't only for cases as exotic as tonight's. It's because the slope is what actually decides which way heat flows, and heat flowing is the thing we really mean, deep down, when we say one thing is hotter than another. Because what is hot, truly, once you strip away the sensation of it? It's this. Put two things together, let them touch, and heat flows from the hotter one into the colder one. Always, the warm mug gives its heat to your cold hands, never the other way. The ice cube pulls heat out of the drink. Hot pours into cold, and never cold into hot, and that one-way flow is the plainest, most operational meaning of the words. Hotter is simply whichever one the heat leaves. Colder is whichever one the heat enters. And here is the quiet, staggering thing, the thing that makes tonight's paradox not a paradox at all, but a plain consequence, once you see it. If you took that little negative temperature cloud of potassium, that billionth of a degree wisp, and you brought it into contact with anything at all, with an ordinary positive temperature, a cup of boiling water, a bar of molten iron, the blazing plasma at the heart of a star, the heat would flow out of the cloud and into that other thing, out of the cold-looking little wisp and into the star. Because by the only definition that ultimately matters, the direction the heat runs, the wisp is the hotter of the two. It would give, and the star would receive. Not because any single atom in it is moving fast. Most of the mechanics of it are gentle and slow, but because of where it sits, on that hill, on the far downhill side, over the top, past infinity, where the true meaning of hot has been turned all the way up and then some. You don't have to believe it tonight. Belief can wait for morning. Just let it be true in the room with you for now, the way a strange dream is true while you're inside it. A cloud colder than the coldest nebula that would nonetheless pour its warmth into the sun. We'll build the whole thing properly, I promise, how they made it, who first glimpsed it more than 70 years ago, why it could only cling to existence for a fraction of a second before it longed to give itself away. And we'll find, near the end, the loveliest twist of all, that the very cage they built to hold these atoms was woven out of the one everyday device that has been quietly living in this same impossible state all along, sitting in drawers and pockets and checkout counters all over the world, and almost nobody who owns one has ever known. But not yet. Not yet. For now, let's just stay with the hill and the flowing heat and the soft dark around you. Let your breathing slow to match the pace of the words. In and out. There's a fence being built at the top of a ladder somewhere far away, in a room full of laser light and patient people. And when it's finished, the meaning of the word hot is going to turn itself inside out. Rest here with me a moment more. The atoms aren't going anywhere. The story keeps. And the strangest, warmest, most impossible part is still ahead of us. Waiting, in no hurry at all, for whenever you're ready to drift a little further in. So, let's talk about ceilings. Think about what happens when you throw a ball straight up into the air. A real ball, in the real world, in a field on a still evening. You throw it, and it rises. You throw it harder, and it rises further. There is, in an ordinary sort of way, no limit to how high you could throw it. In principle, if you had the strength, the ball could leave the atmosphere entirely, escape the Earth's gravity, and travel out into space indefinitely. The kinetic energy you gave it when you released it from your hand could, in principle, grow without bound. You could always add more, always throw harder, always have a faster ball with more energy going upward. Now think about what happens if instead of a field you placed that ball on a staircase. But not an ordinary staircase, an unusual one, with exactly 12 steps and a ceiling just above the 12th. The ball can sit on step 1, step 2, step 6, step 12. Those are its only options. It cannot go higher than step 12. The ceiling is there. It is firm. It is real. No matter how much energy you try to give the ball, it cannot exceed the height of that 12th step, because the ceiling stops it. That ceiling, simple as it sounds, is the thing that makes everything possible. Here is a fact that sounds almost too plain to be worth saying, but which turns out to be the hinge on which this whole story swings. For negative temperature to exist, a system must have a maximum energy state, a top step, a ceiling. There must be something that an atom can occupy that is the highest it can go, with no possibility of going higher. And for ordinary motion, for the kind of thermal energy that lives in the molecules of a gas on your stove, in the air of the room you're lying in tonight, in the cup of water that you may have left on the nightstand, that ceiling does not exist. There is no top step for a molecule of air in your bedroom. If you add energy to it, it moves faster. If you add more, it moves faster still. The kinetic energy of a free particle moving through open space is unbounded. It can always be larger. There is no maximum, and this is exactly why, for centuries, negative temperature seemed like a thing that could not exist for real matter, for the moving, tumbling, colliding atoms and molecules that make up the ordinary world. Because the formula that defines temperature, the relationship between entropy and energy, only produces a negative result when adding energy starts to reduce the number of ways the system can arrange itself. And for that to happen, the system needs to run out of room at the top. You can't run out of room if there is no top. So the question that hung over all of this, from the early days when the idea was first taken seriously, was a practical one. Is there any real system, any collection of atoms or particles in the laboratory that actually has a ceiling, a bounded energy spectrum in the physicist's language, a maximum energy state beyond which no atom can climb, no matter how much you push? And the answer, it turns out, is yes. Several answers, in fact, in several different guises. But we'll come to the earliest of those stories a little later. For now, the point is simply this: Given the right kind of cage, the right architecture, the right rules, a ceiling can be built. And once the ceiling is built, the game changes entirely. Let's follow what happens, step by step, inside a system that has that ceiling in place. Imagine the staircase again, but now it's a system of atoms, and the steps are their allowed energy levels. At the bottom are the low energy states, the ground floor, the comfortable basement. Near the top are the high energy states, pressed up against that invisible ceiling. And at any ordinary positive temperature, something very predictable governs how many atoms sit on each step. This rule is called the Boltzmann distribution, named for the Austrian physicist Ludwig Boltzmann, who worked out its mathematics in the latter half of the 19th century. It is one of the most elegant, most reliable, most quietly powerful laws in all of physics. And what it says is this: in thermal equilibrium, the higher the energy of a state, the fewer atoms you will find in it. Always, without exception. Low steps are crowded. High steps are sparse. The difference isn't small. The number of atoms on a given step falls off exponentially as you go up. The formula that captures this is clean enough to carry in one breath. The ratio of atoms in a high-energy state to atoms in a low-energy state equals e to the power of negative delta E divided by K times T, where delta E is the energy difference between the two levels. K is a tiny constant named after Boltzmann himself, and T is the temperature. The negative sign in the exponent is the crucial one. When T is positive and when E is positive, that exponent is a negative number. And E raised to a negative power is always less than 1, which means the ratio of atoms at top to atoms at bottom is always less than 1, which means there are always fewer atoms at the top. This is not a coincidence. It is a fundamental consequence of what positive temperature means. But now, slowly, gently, watch what happens to that formula if T takes a negative value. If T is negative, then dividing the positive E by it gives a negative divided by a negative, which is positive. The exponent becomes positive, and E raised to a positive power is always greater than 1. The ratio of atoms at top to atoms at bottom exceeds 1, which means more atoms at the top than at the bottom, more atoms in the high-energy states than in the low-energy states. The distribution has flipped. This flipped arrangement has a name, and it is a name you may have heard before in a different context, though perhaps not associated with the word temperature. It is called a population inversion, and it is worth pausing here to really sit with what those two words mean, because they are doing a great deal of work. Normally, the population of atoms, the crowd of them, sits mostly at the bottom in the ground floor states with a thinning out as you climb the energy ladder. An inversion turns that crowd upside down. Suddenly the upper floors are crowded, and the ground floor is nearly empty. These two things, population inversion and negative temperature, are not two separate phenomena with a loose connection between them. They are the same thing, seen from two different angles. If you have a negative temperature, you necessarily have a population inversion. If you have a population inversion in a system at thermal equilibrium within a bounded energy spectrum, you necessarily have a negative temperature. The formula makes them equivalent. They are, in a precise and technical sense, two names for one reality. And this equivalence will matter later, matter quite a lot, when we find out where this state has been quietly sitting, inside an ordinary object, all along. But first, the ordering. This is the part that tends to catch people off guard, and for good reason. Because if you've spent your whole life thinking of temperature as a number on a thermometer that runs from very cold on one end to very hot on the other, the idea of a negative temperature sounds immediately like a colder temperature. Below zero, less than nothing, colder than the coldest. That is the image the language conjures almost automatically. It is completely wrong. Let's trace the actual shape of the temperature scale, because it is not what most people imagine. Start at absolute zero, 0 Kelvin, the coldest temperature that exists or can exist, the floor. Not a floor you can actually reach, as we'll discuss in a moment, but the floor in principle. From there, move upward. 1 Kelvin. 10 A100, the temperature of liquid water. Room temperature. The surface of the sun, around 5,700 Kelvin. The sun's core, around 15 million Kelvin. Further, hotter and hotter, as you add energy without limit. As the system has more and more ways to arrange itself, as entropy climbs and climbs. Temperature rising, climbing toward a number that physics, in its quiet, matter-of-fact way, calls infinity. And now, here is the turn. What happens if you keep going? The answer is, the temperature passes through infinity. Not around it, not past some enormous but finite number. It genuinely passes through positive infinity, and, in doing so, wraps around to negative infinity. Like a number line that has been bent into a circle, where the two ends, positive infinity and negative infinity, meet at the same point. You go up and up through the positive numbers, you reach infinity, and the very next step brings you out the other side at negative infinity. And from negative infinity, you climb back upward through the negative numbers, negative millions, negative thousands, negative tens, until you approach a limit that physicists write as negative zero. Not zero itself, but the negative approach to zero. And that limit, that negative zero endpoint, is the hottest state that a negative temperature system can occupy. So the full ordering of temperatures, from the coldest state to the hottest, looks like this. Absolute zero is the coldest. Positive temperatures climb from there to infinity. Negative infinity, the other side, is warmer still. And as you move from negative infinity upward through the negative values toward negative zero, you are climbing toward the hottest possible state a bounded system can reach. Negative temperatures sit above positive infinity on this scale. They do not sit below zero, they sit above everything. This means that if you placed a negative temperature gas, a cloud of atoms in an inverted population, pressed against that energy ceiling, next to a pot of boiling water, heat would flow out of the gas and into the water. If you placed it next to the surface of the sun, heat would flow out of it and into the sun. If you placed it next to the sun's core, where temperatures reach 15 million Kelvin, heat would still flow out of the gas and into the core. This is because heat, by the most fundamental operational definition we have, flows from hot to cold, from higher temperature to lower. And by the thermodynamic ordering, the negative temperature gas sits above positive infinity, above everything, on that scale. It is hotter, in this precise and real sense, than anything that carries a positive temperature, including the core of a star. Now I want to offer you something that might help dissolve the strangeness, rather than just asserting it. A different variable, a different way of labeling the same physical reality that makes the wraparound ordering visible without the paradox. Physicists sometimes work not with temperature T, but with a quantity called coldness, sometimes labelled with the Greek letter beta, and it's defined simply: beta equals 1 divided by temperature. just the reciprocal. If T is large and positive, beta is small and positive. If T approaches positive infinity, beta approaches zero from above. If T becomes negative, crossing over from positive infinity to negative infinity, beta crosses zero and becomes small and negative. And as T climbs from negative infinity toward negative zero, beta grows more and more negative, heading toward negative infinity. Here is the beautiful thing about beta. It runs smoothly, continuously, and monotonically. From large positive values at absolute zero, it decreases through zero at infinite temperature and keeps decreasing into negative territory as you enter the negative temperature regime. There is no jump, no discontinuity, no wraparound that looks strange. The variable just keeps getting smaller. The confusion was an artifact of working with T, which has that inversion built into it. Because T is defined as the reciprocal of something, not as the something itself. Beta is what makes the shape of the physics visible without distortion. And in beta's language, the ordering is simply this. Very cold systems have very large positive beta, very hot systems have large negative beta, and the negative temperature gas of the 2013 experiment, which we'll spend real time with a little further on, sits at a very large negative beta, meaning very small coldness, meaning very hot indeed. There is no mystery in the math, only in the name we happened to give it. A quick reminder, just while we're pausing here at this seam in the story, after years of lying awake with a racing mind, deep sleep finally became possible for me. Learning comes easier now, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made that possible, the link is in the pinned comments. And now, gently, a thing that needs to be said clearly, because the name of this phenomenon, negative temperature, below absolute zero, as the press reports of 2013 tended to call it, carries inside it a misconception that has been travelling around ever since. Negative temperature does not mean colder than absolute zero. Absolute zero is not threatened by any of this. The third law of thermodynamics, the law that establishes absolute zero as an unreachable lower limit, a destination you can approach but never reach, remains completely intact. Negative temperature does not violate it, does not sidestep it, does not represent a discovery that the third law was wrong. Everything the third law says remains true. Absolute zero is still the coldest, still unreachable, still the floor. The confusion arises from the way the temperature scale is labelled. 0 Kelvin sits at one end of the positive temperature axis, and negative temperatures sit on the other side of a different boundary, not below zero, but above infinity. They are reached by a path that goes through positive values, climbs to positive infinity, and then wraps to the negative side. They never pass through absolute zero to get there. They never go below zero in any meaningful physical sense. The journey from a positive temperature to a negative one passes through the hottest possible state, positive infinite temperature, not through the coldest. Think of it this way, if it helps. Imagine a clock face with absolute zero at the 6 o'clock position and the temperature scale running clockwise from there through positive values, climbing toward noon at the top, which is positive infinity. If you keep going past noon, clockwise you arrive at the 1 o'clock and 2 o'clock positions. Those are negative temperatures, large negative values, still very hot. And the 6 o'clock position from the other side, what you might call negative zero, if you're approaching it from the negative direction, is the hottest point on the whole face. The hands never go backwards through 6. They go forward through 12. Absolute zero remains untouched. The third law holds. And the negative temperature gas, for all its paradoxical name, is not a cold thing that somehow broke the rules. It is a hot thing, almost inconceivably hot by the thermodynamic reckoning, that happens to carry a number with a minus sign in front of it. And that minus sign is, as we've seen, simply the mathematical consequence of an energy distribution that has turned itself upside down. More atoms at the top of the ladder than at the bottom. The Boltzmann distribution flipped. Entropy decreasing as you add energy instead of increasing. The slope of the entropy versus energy curve going negative instead of positive. Every piece of language points to the same physical reality from a different angle, and the reality itself is not mystical at all. It is, in its own quiet way, quite logical. Even inevitable, given the right conditions, which brings us back, slowly, to the ceiling. Because all of this, the population inversion, the flipped Boltzmann distribution, the negative slope of entropy, only becomes possible if the system has a bounded energy spectrum, a maximum energy state. That 12th step at the top of the staircase, pressed against the ceiling, and for ordinary matter, for the molecules of air in the room where you're resting tonight, for the water in that glass, for the steam rising from a kettle, for the gas in a star, there is no such ceiling. A free particle's kinetic energy is unlimited. You can always push it faster. You can always give it more. The ladder has no top step. So no matter how much energy you pour in, there will always be lower states with more atoms in them than higher states, because there is always something higher, always more room to spread into, always new entropy to gain. This is why negative temperature seemed, for so long, like a purely theoretical game. Interesting on paper. Impossible in practice, a thing that the equations permitted but the universe did not. You'd need a substance with a hard upper limit on how much energy any part of it could hold, and where exactly would you find such a thing? The answer, as it turns out, came in stages. First, in a very particular kind of quantum system, one that has very few energy states to choose from. Then, over decades, in new and more elaborate structures, and finally, just over a decade ago, in a gas, in actual atoms moving through actual space, which was when the story became impossible to ignore. But the key to each of those steps was the same. The ceiling, the bounded spectrum, the top step on the ladder that stops the atoms from simply dispersing upward forever and forces the energy distribution into a corner where it has no choice but to invert. For ordinary gas, with no ceiling, the distribution never inverts. More atoms always sit on lower steps than higher ones. Temperature always carries a positive sign. This is not a coincidence or a convention. It is a direct consequence of the unbounded energy available to free particles. An infinite staircase can never be more crowded at the top than at the bottom, no matter how much energy you add, because there is always more room above. And this is one of the most important facts in the whole story, not because it is complicated, but because it is exactly backwards from the way the 2013 headlines read. Those headlines said, "Scientists push gas below absolute zero." They made it sound as if a gas had done something ordinary gases might do, only more extreme. A gas, but colder. More of the same, but pushed further. But that was not what happened at all. What happened was that a gas had been made to do something that gases, in principle, are not supposed to be able to do. Something that requires a ceiling that ordinary gases do not have. something that was only made possible by building, from laser light of all things, an extraordinary artificial structure that provided exactly the bounded energy spectrum that free space never provides. The ceiling wasn't found in nature, it was constructed. And the way it was constructed, the specific kind of cage that gave those 100,000 potassium-39 atoms their top step, their hard limit, their energy ceiling, is a story that winds through more than 60 years of physics, through nuclear spins and crystals and cold gases and laser-woven lattices, and through some of the most careful, patient, precise experimental work that has ever been done in a laboratory. But that history and the details of that construction belong to the next part of the journey. The part where we meet the people who first glimpsed this possibility, who first flipped a system into negative temperature in 1951 with nothing but a crystal and a magnetic coil and a very quiet kind of courage. The part where we trace how the idea moved from the realm of nuclear spins, tiny, bounded, almost invisible, out into the open air of a gas, where billions of atoms could suddenly find themselves all at once in the hottest state that thermodynamics allows. We have the definitions now. We have the shape of the scale. We know what the ceiling means and why it matters. We know that negative temperature is not colder than zero, but warmer than infinity, that it is population inversion by another name, that it is a consequence of entropy bending in the wrong direction when a bounded system runs out of room to grow. And we have one question still hovering in the room with you, quiet but insistent, the one that was placed gently in the air a little while back. You already own a device that runs on negative temperature. You may have used it today, without knowing. There is probably one within a few meters of where you are lying right now. That answer is coming. It is not far. But it belongs after the history, after the people and the crystals and the cold gas and the laser light that brought it all together, because when you hear it in that order, with all the pieces in place, it will land differently. It will land with the feeling not of a clever fact, but of a recognition. The way you recognize a face you've been looking at without seeing. Something that was always there, just waiting for you to understand what you were looking at. So rest there for a moment in the soft, warm familiarity of the unexpected. The ceiling exists, the distribution can flip, the scale wraps around. The third law is fine, absolute zero is fine. All the familiar furniture of thermodynamics remains exactly where it was, and yet, within those rules, something extraordinary is allowed, something that a system of atoms with the right kind of cage can become, briefly, under the right conditions. The ceiling is the key. And somewhere in a room lit by the cold blue-white glow of carefully tuned lasers, in Munich, a little more than a decade ago, a group of very patient scientists built exactly that ceiling out of standing waves of light, and filled it with the coldest gas you could imagine, and then, in a fraction of a second, turned everything upside down. But that is a story for the part of the night that is still ahead of you. For now, let the shape of the thing settle in. The staircase with 12 steps and a ceiling. The crowd of atoms, normally clustered at the bottom, suddenly, impossibly, more numerous at the top. The temperature that the formula spits out carrying a minus sign, not because the system is cold, but because the entropy is doing something that entropy, in ordinary matter, simply does not do. Something that only becomes possible when there is a ceiling, when there is a top step, when the ladder has an end, and outside, wherever you are, a window, a lamp. A clock. The ordinary world continues its ordinary boltzmann business, with more atoms always at the bottom than the top, with entropy always climbing when you add energy, with temperature always positive, with everything exactly as it should be, and not a ceiling in sight. Except perhaps for that one thing on your desk, or in your bag, or in the drawer across the room. That quiet little exception, but not yet. Let the ceiling sit with you for now. Let the wraparound temperature scale settle like a strange map of a country you're just beginning to recognize. Let beta, that smooth, continuous, undramatic reciprocal, show you that what looked like a paradox was only a choice of coordinates, and that a different choice makes the whole thing lie flat and calm, with no wrinkle, no jump, no seam. Let absolute zero stay where it is, at the cool bottom of the map, unthreatened, unreachable, exactly as the third law always promised it would be. And somewhere above infinity, in the thermodynamic night, the negative temperature gas sits, radiating warmth into anything it touches, burning hotter than anything in the universe, with a positive sign. Made of 100,000 atoms that are each no bigger than a pinprick of almost nothing, each moving, each carrying their impossible distribution, the crowd pressing upward against the ceiling. Patient, warm, waiting, so let us go back. Not to the gas itself, not yet, not to Munich, not to 2013, but further, to the beginning of the idea, to the moment when someone first looked at a system pressed hard against its own energy ceiling and thought, wait. Something unusual is happening here. And then, let me write it down carefully. Because ideas like this do not arrive all at once. They arrive the way most true things arrive, in pieces over decades, from different hands in different rooms, each one doing a small part of the work without quite seeing the whole shape. And so if you are comfortable wherever you are, if your eyes are soft, we can take our time with the history. There is no rush. The gas is patient, and the history, once you know it, makes the 2013 experiment feel less like a sudden miracle and more like a long, slow arrival, the last step of a walk that started in 1949, in the notebooks of one of the strangest and most brilliant minds in 20th century physics. His name was Lars Onsager. He was Norwegian by birth, American by profession, and by temperament something entirely his own, famously difficult to follow in seminars, famously prone to thinking thoughts that nobody else in the room was yet equipped to understand. He won the Nobel Prize in Chemistry in 1968 for work he had done in the 1930s on irreversible thermodynamics. Work so far ahead of its time that the recognition took 30 years to arrive. That is the kind of person Lars Onsager was. In 1949, he was thinking about fluids, specifically about turbulence, about the way rotating vortices behave in a flat, two-dimensional fluid, the kind of idealized fluid a theorist can write equations for and then watch, on paper, as it moves. Vortices in two dimensions are strange objects. They interact with each other in complicated ways, attracting, repelling, clustering, scattering, and Onsager wanted to understand what happens to them statistically. What is the equilibrium state of a large collection of these vortices? The answer he found was unexpected. He published it in the supplement of a journal called Nuovo Cimento, a brief, compressed paper, the kind that takes a paragraph to state something that takes years for everyone else to unpack. What he showed was that in a two-dimensional fluid, the energy of the vortex system is bounded from above. There is a maximum total energy the collection of vortices can hold. And he worked out, carefully, what happens near that upper bound. Near the top, the system starts to behave in a way that is thermodynamically upside down. Entropy, the measure of how many arrangements are available, begins to decrease as you add energy. The slope that defines temperature, that ratio of entropy's response to energy, goes negative. And Onsager wrote, with characteristic terseness, that the statistical mechanics of such a system implies a negative absolute temperature. He was not talking about atoms whose kinetic energy had been inverted. He was talking about abstract vortices in an idealized fluid. But the physics was there, clear as anything, in 1949, in a paper most physicists did not fully read, in a journal supplement most people did not pick up. The idea needed someone to take it seriously on its own terms. 2 years later, someone did. Edward Purcell and Robert Pound, working at Harvard, were not thinking about turbulence or vortices. They were thinking about nuclear magnetic resonance, about the behavior of atomic nuclei in a magnetic field. And they were, in the early 1950s, among the most careful experimental physicists alive. Purcell would go on to share the Nobel Prize in Physics in 1952 for his contributions to nuclear magnetic resonance, work that, decades later, would become the basis of MRI scanning. He knew his instruments. He knew what his data was telling him. The experiment they ran in 1951 was, in concept, almost beautifully simple. Almost, take a crystal of lithium fluoride. Lithium fluoride is an ordinary-looking white powder, the kind of thing you might see in a laboratory shelf with a label and a stopper. It is ionic, crystalline, regular, and, crucially, the lithium nuclei inside it have a property called spin, a quantum mechanical angular momentum that, in a magnetic field, is forced to align either with the field or against it, like tiny compass needles. Aligned with the field is lower energy. Aligned against it is higher energy. And at thermal equilibrium, the way you would expect, more nuclei are in the low-energy state than the high-energy state. The Boltzmann distribution working quietly, reliably, as it always does. The energy of these spin states is bounded. There is a lower limit, all spins aligned with the field, and an upper limit, all spins aligned against it. The spectrum has a top. And that, as Onsager's work had suggested, and as the statistical mechanics demanded, is the prerequisite for the possibility of something strange. What Purcell and Pound did was this. They placed the lithium fluoride crystal in a strong magnetic field and allowed the nuclear spins to come to equilibrium with their surroundings. Low-energy states populated. High-energy states sparse. Boltzmann distribution, quiet and ordinary. Then, very quickly, faster than the spins had time to respond, faster than they could follow, they reversed the magnetic field. Think about what that means for a moment. The field flipped. What was the low-energy direction is now the high-energy direction. What was the high-energy direction is now the low-energy direction. The spins, still frozen in their old arrangement, now find themselves in the wrong places. The majority that had been sitting comfortably at the bottom of the energy ladder now find themselves at the top, and the sparse minority that had been at the top now find themselves at the bottom. In a single sharp instant, the population had been inverted. And so the spin system, isolated from the larger crystal's other vibrations for a brief window of time, several seconds, which in this context is a very long time indeed, sat in an inverted state. More spins in the high-energy configuration than in the low-energy one. The entropy of the spin system, which had been climbing normally with the field's energy, was now in the wrong regime. Adding energy to this inverted spin system would decrease entropy, not increase it. The slope of entropy versus energy was negative. The temperature of the nuclear spin system was, by the strict thermodynamic definition, negative. They measured it. It was real, and it lasted for several seconds before the spins began to talk to the rest of the crystal, leaking their inverted energy away, relaxing back toward equilibrium. Several seconds. That might not sound like much, but when you are holding a piece of matter in a state that sits on the far side of thermodynamic infinity, hotter, by the rules of the mathematics, than anything with a positive temperature, several seconds is astonishing. It is enough to measure. It is enough to know it is really there. Purcell and Pound published their result in Physical Review in 1951, volume 81. It was careful work. It was real. And it established for the first time that negative absolute temperature was not a theoretical abstraction or a quirk of Onsega's vortex mathematics. It was something you could actually hold, briefly, in a laboratory, something that existed in matter, in measurable, describable, real physical form. But the theoretical foundation was not yet complete. The concept existed. The experiment existed. What was still missing was a clear, rigorous statement of what negative temperature actually meant for thermodynamics as a whole, how it fit into the laws, what its consequences were, how to think about it without either dismissing it or overstating it. That work fell to Norman Ramsey. Ramsey was, by the mid-1950s, one of the leading figures in the precision measurement of atomic and molecular properties. He would eventually win the Nobel Prize in Physics in 1989 for the method of separated oscillatory fields, a technique of extraordinary precision that became the basis of modern atomic clocks. That was his Nobel. But in 1956, he was doing something quieter and more foundational. He sat down and worked out the thermodynamics. His paper, Thermodynamics and Statistical Mechanics at Negative Absolute Temperatures, published in Physical Review in 1956, volume 103, is the document that placed the whole idea on solid ground. It is not a long paper by modern standards, but it is precise. And it establishes, carefully and without ambiguity, several things that are still true and still taught. It establishes that negative temperature is a legitimate thermodynamic state, not a glitch, not an artifact, not a figure of speech. A real thermodynamic state, consistent with the laws of thermodynamics, properly defined by the relationship 1T Carlas, SE, and carrying specific, predictable physical consequences. It establishes the correct ordering, not plus 0K at the bottom, climbing to plus at the top, and then cold negative temperatures below zero. No, the correct ordering from coldest to hottest is absolute zero at one end, warmer and warmer positive temperatures climbing toward positive infinity, then wrapping around. As if the number line bent into a circle and the two infinities touched, negative infinity, which is the same physical state as positive infinity, the infinite temperature state of maximum disorder. And then, warming still, negative temperatures climbing upward from negative infinity toward negative zero, which is, thermodynamically, the hottest state, the state of pure, total, maximum energy with no room left to go higher. Coldest to hottest, in one smooth arc, plus zero, plus small, plus large, plus tarkless, large, small, zero. Ramsey wrote it down clearly. He showed that a negative temperature system, when placed in thermal contact with any positive temperature system, will always push heat outward. Always, because heat flows from hotter to cooler, and negative temperatures are, by this proper ordering, hotter than any positive temperature, hotter than boiling water, hotter than the surface of the sun, hotter than the core of a star. The sign on the number is negative, but the physical meaning of the word hot is this thing will warm you, not the other way around. And Ramsey showed that none of this violates the third law of thermodynamics. Absolute zero remains unreachable, unthreatened, exactly where it always was. Negative temperature is not approached by cooling, it is not reached by pushing a system down past zero, it is reached, and this is the key, by pushing a bounded energy system up past positive infinity. By loading so much energy into a system with a ceiling that the entropy starts to fall with each additional joule, by arriving at the far side of hot through the only door that leads there, an energy spectrum with a top. Without a ceiling, you cannot get there. With a ceiling, you can. That was 1956. The framework was in place, the physics was understood. And then, for a long time, negative temperature lived in a particular corner of physics, nuclear spin systems, bounded quantum states, the tidy world of magnetic resonance and spin thermodynamics, real, verified, interesting to specialists. But confined, because finding a natural system with a bounded kinetic energy, a gas whose actual motion, whose actual movement through space had a maximum value, seemed almost impossibly difficult. Normal matter does not come with ceilings on its motion. A gas molecule can always move faster. The kinetic energy of atoms in free space has no top, and so the question that sat quietly through the second half of the 20th century was this: could you ever make a gas, not a spin system, not an electronic state, not a magnetic resonance experiment, but actual atoms with actual velocity moving through actual space, sit at a negative temperature? Could you flip the kinetic motional degrees of freedom into an inverted state? For a long time the answer was probably not. Not for a gas, not for something whose motion was its temperature, because the ceiling was missing, until someone figured out how to build one. The place where that happened was Munich. The year was 2013. And the key, as it turned out, was light. Ulrich Schneider and Immanuel Bloch were the leaders of the team. Schneider was based at Ludwig-Maximilian University Munich. Bloch was at the Max Planck Institute of Quantum Optics, also in Munich, one of the most celebrated centers for quantum physics in the world. They were working in a field called ultra-cold quantum gases, which involves cooling clouds of atoms to temperatures so close to absolute zero that the atom's quantum nature dominates their behavior. And strange collective phenomena, superfluidity, Bose-Einstein condensation, the quantum of motion itself, become visible to experiment. Ultra-cold physics by 2013 was a mature and extraordinarily precise field. Researchers had learned to cool atoms to billionths of a degree above absolute zero to trap them in magnetic and optical fields, to manipulate their interactions with astonishing control. The toolkit was rich, and Schneider, Bloch and their colleagues, the team listed on the paper is Braun, Ronzheimer, Schreiber, Hodgman, Rom, Bloch and Schneider, looked at that toolkit and saw something. They saw that they could build a ceiling. The ceiling would be made of light, specifically of something called an optical lattice. And if you have never encountered an optical lattice before, let me take a moment with it, because it is one of the genuinely beautiful constructions in modern physics. Imagine two laser beams traveling toward each other from opposite directions, meeting in the middle. When waves meet like this, they interfere, they add together and cancel in a regular repeating pattern of crests and troughs. With light, this interference creates a standing wave, a regular fixed pattern of bright and dark regions that does not move, bright, dark, repeating in space like a striped fabric made of light. Now, atoms are not neutral to this pattern. A neutral atom, placed in a varying intensity of light, will be attracted toward the bright regions, or, depending on the tuning of the laser, toward the dark regions. The light creates potential energy wells. The atom settles into the bottom of a well, like a marble resting in a bowl. And because the wells are created by the regular interference pattern of the laser beams, they are arranged in a regular, repeating grid. An optical lattice, in 3 dimensions, is an egg carton made of light. Each little hollow in the egg carton is a potential well where an atom can sit. The atom is not free to move anywhere, it is confined to the wells, and it can hop between adjacent wells, but only within the constraints the lattice imposes. And here is the crucial thing. An atom moving in an optical lattice does not have unlimited kinetic energy. The band structure of the lattice, the allowed energy levels for an atom confined to these periodic wells, has a top, a maximum, a ceiling. The atom can be at the bottom of the energy band, sitting quietly in the lowest state. Or it can be at the top of the energy band, packed into the highest motional state the lattice allows. But it cannot go further. The lattice, unlike free space, does not let the atom accelerate without bound. The ceiling was real. The precondition was satisfied. And so the experiment they designed was in structure a direct descendant of what Purcell and Pound had done in 1951 with nuclear spins, but translated into the language of ultra-cold motional physics. Start the atoms in the low-energy corner of the lattice. Then, in a single controlled step, flip them into the high-energy corner. Invert the population. Create the upside-down Boltzmann distribution, with more atoms crowded at the top of the energy band than at the bottom. The gas they used was potassium-39, a specific isotope of potassium, chosen for its amenable quantum properties. They cooled it, using laser cooling and evaporative cooling techniques, to a temperature of billionths of a degree above absolute zero. Then they loaded it into the optical lattice. Roughly 100,000 atoms arranged in the wells of the light crystal, sitting near the bottom of the energy band, cold and quiet. And then they flipped it. But here the experiment gets subtle. Because flipping the atoms into the high-energy corner is not as simple as reversing a magnetic field, as Purcell and Pound had done. In a gas of atoms, unlike in isolated nuclear spins, the atoms interact with each other. They push against each other. And when you try to pile atoms into the high-energy corner of an energy band, those repulsive interactions want to pull the system apart, to scatter the atoms out of the inverted state before it can stabilize. This is where the Feshbach resonance comes in. A Feshbach resonance is a remarkable tool. It is a way of tuning, using an applied magnetic field, the strength and even the sign of the interactions between ultracold atoms. Repulsive interactions, which push atoms apart, can be dialed continuously through zero to attractive interactions, which pull atoms together simply by adjusting the magnetic field to a particular value. The name comes from Hermann Feshbach, an American physicist who described the underlying collision physics in the 1950s. The technique, in practice, gives experimenters an extraordinarily precise control over how atoms in an ultracold gas relate to one another. What the Munich team did in a single coordinated step was this: they inverted the trapping potential of the lattice, flipping the wells upside down so that the high-energy corner became the energetically preferred position, and simultaneously, using the Feshbach resonance, they switched the interactions between the potassium atoms from repulsive to attractive. Both switches at once. Both handles turned at the same moment. The inversion of the potential pushed the atoms up toward the high-energy corner of the energy band. And the switch to attractive interactions, atoms now pulling gently toward each other rather than pushing apart, stabilized them there. Without that switch, the inverted gas would have been like a crowd of people all pushing each other outward on a crowded dance floor, chaotic, dispersing. Unstable, with attractive interactions, the crowd could press together, lean on each other, hold the inverted state against the tendency to scatter, and it worked. The atoms sat in the high-energy corner of the lattice band. The population was inverted. More atoms were in high-energy states than in low-energy states, exactly as the Boltzmann formula says must happen when the temperature is negative. When the ratio of high to low state populations, given by the exponential of minus the energy difference divided by the product of the Boltzmann constant and the temperature, exceeds 1 only because T is a negative number. The gas was thermodynamically at a negative absolute temperature. The number the team put on it, the magnitude, the scale, was a few nanokelvin, a few billionths of a degree. But on the negative side of the temperature axis, a few negative nanokelvin. Take a moment with that. A nanokelvin is a billionth of a degree above absolute zero. It is one of the coldest things that can exist. The core of the Sun is roughly 15 million degrees Kelvin, 15 billion nanokelvin, roughly the coldest natural place in the known universe. A nebula called the Boomerang Nebula sits at about 1 Kelvin, 1 billion nanokelvin. The atoms in the Munich experiment were at 1 nanokelvin in magnitude, which is colder than the coldest nebula by a factor of 1 billion. And yet those same atoms, by the thermodynamic definition, by the rule that says heat flows from hotter to cooler, by the rule that says temperature is the slope of entropy with respect to energy, were hotter than anything in the universe with a positive temperature. Hotter than the Boomerang Nebula, hotter than the surface of the Sun, hotter than the core of a star, hotter than any positive temperature, because they were on the other side of infinity, in the regime where the number line wraps and positive infinity and negative infinity are not opposites, but neighbours. The coldest-looking object ever made in a laboratory. And simultaneously the hottest thermodynamic object in the universe, both things at once, depending on which aspect of the physics you are measuring. The result was published in the journal Science in January 2013. The paper was Braun, Ronzheimer, Schreiber, Hodgman, Bloch and Schneider. Volume 339, pages 52 to 55. A brief paper, as these things go. Precise, careful, and carrying a claim that would make headlines around the world, and also, as we will see in a little while, spark a genuine scientific argument that is not entirely settled even now. But before that argument, before the controversy and the question of whether the word temperature itself is the right word, let us sit for a moment with the difficulty of what they had actually done. Because the experiment was not just conceptually remarkable. It was, in practice, extraordinarily hard to hold together. The gas was metastable. That word, metastable, is one of those words from physics that sounds technical but contains a very human kind of meaning. Something metastable is stable, but not really. It is stable in the way a ball balanced on the very tip of a hill is stable, technically at rest, technically in equilibrium, but one small nudge away from rolling in either direction. It is stable in the way a soap bubble is stable, beautiful, complete, real, but with a lifetime measured in moments before the world outside it reasserts itself. The negative temperature gas was metastable, because of something we established earlier, something that comes directly from the thermodynamic ordering Ramsey worked out in 1956. A negative temperature system, when it encounters any positive temperature system, will push heat into it. Always, because the negative temperature state is hotter and heat flows from hot to cold. And the problem is, the laboratory is full of positive temperature things. The optical lattice is built from laser light that interacts with the outside world. The vacuum chamber has walls. The atoms, however cold they are in magnitude, will eventually find a way to talk to those walls, to the photons bouncing through the room, to the vibrations in the equipment, and the moment they do, the energy flows. The inverted population relaxes. The atoms that had been pressed into the high-energy corner of the energy band begin to slide back toward the bottom. The Boltzmann distribution, patient and inexorable, reasserts itself. The negative temperature ceases. The lifetime of the inverted state, the window during which the gas sat at negative temperature before the world outside it drained the inversion away, was measured in hundreds of milliseconds. Fractions of a second. Hundreds of milliseconds is, in the world of ultra-cold physics, actually a very reasonable experimental lifetime. Long enough to probe, long enough to measure the momentum distribution and verify that the atoms were crowded into the high-energy corner of the band, not the low-energy one. Long enough to confirm that the system behaved, thermodynamically, exactly as a negative temperature system should. Long enough to know that it was real. But fractions of a second is also, if you are lying there, imagining what it would feel like to hold such a thing in your hands, heart-breakingly brief. The hottest object in the universe, radiating its heat into anything it touched, too fragile to last a single breath. That fragility is not a failure. It is, in a sense, the point. The negative temperature state is not stable because the universe around it is always warmer, in the thermodynamic sense, always more willing to accept the energy the inverted gas is pressing outward. The metastability tells you the state is real. It tells you the heat is flowing in exactly the right direction. From the hotter thing toward the cooler thing, from the negative temperature gas toward the positive temperature surroundings. The universe doing what the universe does. What kept the gas alive as long as it did was the design of the trap itself. The optical lattice and the attractive interactions were not just the mechanism for creating the negative temperature state, they were also the armor that protected it. The lattice provided the energy ceiling that made negative temperature possible in the first place. The attractive interactions stabilized the atoms in the inverted configuration against scattering. Both handles, the depth of the lattice wells, the sign of the interactions set by the magnetic field via the Feshbach resonance, were working together, one creating the condition, the other holding it in place, and even so, the world outside won. Within hundreds of milliseconds, the inversion was gone. Schneider and Bloch and their team measured what they could in that window. They used time-of-flight imaging, releasing the atoms from the trap and watching how they spread out, reading the momentum distribution from the way the cloud expanded. In a normal cold gas, the cloud expands into a soft, smooth distribution with most atoms near the center, low momenta, low energies, the Boltzmann shape you expect. In the inverted gas, the distribution was different. The atoms spread toward the edges first. The high momentum corners of the distribution were more populated than the low momentum center. The cloud was, in momentum space, upside down. That image, the inverted momentum distribution of 100,000 potassium atoms in a Munich laboratory, published in Science in January 2013, is the experimental fingerprint of negative absolute temperature for the motional degrees of freedom of a gas. The first time, in the history of physics, that the actual kinetic motion of real atoms had been placed in a thermodynamically negative temperature state. And there is something else worth holding on to as we let this sink in. Purcell and Pound did it with nuclear spins in 1951. Ramsey placed it on rigorous thermodynamic footing in 1956. The laser industry quietly relied on a close cousin of the phenomenon every day, decade after decade, in every gain medium ever built. The concept had been real and known and used in its various forms for 60 years before the 2013 experiment. What Schneider, Bloch and their team added was not the first instance of negative temperature. They were clear about that. What they added was the first instance in the one domain where it had seemed hardest to reach. The actual, physical, real space motion of a gas. The translational, kinetic, motional energy of atoms flying through space. Not spins, not electronic states, not any of the bounded internal degrees of freedom where negative temperature had lived comfortably since 1951. The motion itself. The thing that, in the naive version, temperature was supposed to measure. And they reached it by building a ceiling out of light, by trapping atoms in an egg carton made of laser interference, by flipping two handles at once, the potential and the interactions in a single coordinated step that turned a gas sitting at the bottom of its energy band into a gas sitting at the top. The technique was elegant. The result was clean. The physics was unambiguous. Whether the word temperature was the right word for what they had made, that question, it turns out, is more complicated. And it opens into a debate that is still alive, still running, still being argued in the pages of physics journals by careful and thoughtful people who disagree not about what the experiment showed, but about what language best describes it. But that is a story for a little later. For now, let it be enough to say, it was there, in Munich, in January 2013. For hundreds of milliseconds, a gas of 100,000 potassium atoms sat at a negative absolute temperature, the hottest thermodynamic state in the universe, held alive by light and magnetism and the careful hands of people who had spent years learning how to build things at the edge of what was possible. And then it relaxed, and the world went on, and the paper was published, and the headlines, quite reasonably, went a little wild. If you are still awake, wherever you are, if the lamp is still on, if the night is still around you, you have now followed the full path. From Lars on Seger's 1949 paper on vortices in two-dimensional fluids, which first showed that bounded energy systems could have negative temperatures, to Edward Purcell and Robert Pound in 1951, who took a crystal of lithium fluoride, reversed its magnetic field faster than the nuclear spins could follow, and held a piece of matter at negative temperature for several seconds. To Norman Ramsey in 1956, who put the whole framework on rigorous mathematical footing, established the correct thermodynamic ordering from coldest to hottest, and showed that negative temperature was consistent, not merely consistent, but a necessary consequence of the proper definitions. To Munich in 2013, where Ulrich, Schneider and Immanuel Bloch and their colleagues made an optical lattice from interfering laser beams, loaded it with potassium-39 atoms, threw two switches at once, and watched the impossible happen. 64 years from Seger to Braun et al. 64 years of the idea moving, slowly and carefully, from an abstract result in a vortex calculation to a measured, published, reproducible fact in a laboratory. The way ideas move in physics, not in sudden leaps, but in long, patient accumulations, each generation doing its part. Each experiment building on the one before. You are somewhere in that timeline now. You are on the far side of the 2013 result, with the history behind you, with the physics of the experiment settled in your mind, with the ceiling and the lattice and the Feshbach resonance and the metastability all lying flat and clear. And there is still something left to say, something about where you have seen this before, or rather, where you use it every day, without knowing. The gas in Munich lasted hundreds of milliseconds. The thing in your bag or on your desk has been running on the same principle, continuously, for decades. That quiet little exception, still waiting. So, let's talk about that quiet little exception. It's been sitting there this whole time, patient as anything. Every time you've scanned a grocery item, or played a disc, or sent a message over fibre optic cable, or pointed a small red dot at a wall to entertain a cat, it was there. Running, doing its thing. Operating on exactly the physics we've been slowly walking through tonight, in exactly the configuration we've been describing. The thing about physics is that its strangest corners have a way of turning out to be everywhere. You think you've found something exotic, something that lives only in a Munich basement at a billionth of a degree. Something that requires a team of researchers and a decade of preparation and a set of laser beams arranged with extraordinary precision. And then you look down at your desk, or into your bag, or at the shelf in the living room, and you realize, oh, it was already there. Let me show you what I mean. You remember the mechanism. You remember what it takes to reach a negative temperature. You need a system with a ceiling, an upper bound on its energy, so that the energy spectrum is bounded from above. You need more atoms in the high-energy states than in the low-energy states. You need the inverted population. And when you have that, and when the system is in something like equilibrium within itself, then by the definition of temperature, the slope of entropy with respect to energy, the temperature is negative. The Boltzmann factor for relative populations, the ratio of atoms up high to atoms down low, exceeds 1. The thing is upside down, in exactly the right way. Now, think about how a laser works. Not in detail, just the broad shape of it. A laser works by taking atoms, or molecules, or electrons in a solid, whatever the active medium is, and pumping them into an excited state. You push energy in from a flash lamp, from an electrical current, from another light source, and the medium absorbs it, and the atoms climb up into a higher energy configuration. So far so ordinary, that's just absorption, that's just what matter does when you shine light on it. But here is the part that makes a laser a laser. For the light to be amplified, for the device to work at all, for the beam to emerge, there must be more atoms in the excited state than in the ground state, more atoms up high than down low. The inverted arrangement, the population inversion. That is not a metaphor. That is not an analogy. That is the literal physics of how every laser operates without exception. Stimulated emission, the process by which one photon causes an excited atom to release a second photon of identical energy and phase, the cascade that becomes the beam, only produces net amplification when the population is inverted. When the gain medium has more atoms in the high-energy state than the low-energy state, the light passing through gets brighter. When it doesn't, when the normal Boltzmann distribution holds, with more atoms at the bottom, the light gets absorbed. You get a dark material, not a laser. So to have a laser, you must have population inversion. And population inversion, as we worked through carefully a little while ago, is another name for negative temperature, which means every laser is running on a medium at a negative absolute temperature. Every one. the red light in a barcode scanner at the checkout, the diodes in a fiber optic cable carrying your internet connection, the disc reader in a DVD player, the green dot in a laser pointer. Every tool that uses stimulated emission to amplify light has, sitting inside it, a gain medium in which the population is inverted, the Boltzmann distribution is upside down, and the temperature, in the strict statistical mechanical sense, is negative. It has been there all along, for decades, operating quietly, reliably, in billions of devices, in homes and hospitals and offices and laboratories on every continent. Not a curiosity, not a billionth of a degree experiment in a Munich basement. A commercial reality, mass-produced, available for a few euros at any electronics shop. This is what Ulrich Schneider's team meant when they said, very clearly, in 2013, that their achievement was not the first negative temperature in history. It was the first negative temperature in the motional degrees of freedom of a gas. The atom's actual physical movement, their kinetic energy in real space, was in the inverted distribution. That had never been done before. In the laser, the inversion lives in the internal energy levels, the electronic states of the atoms or molecules in the medium, the discrete rungs on the quantum ladder of how the electrons are arranged around the nucleus. The atoms can be sitting still, and their electron states can still be inverted. In 2013, Schneider and Bloch and their colleagues went further. The atom's external motion through space, the very movement of the particles themselves, was in the negative temperature state. That distinction matters, and it is a genuine achievement. But it should not make the laser connection feel lesser. If anything, it makes it more remarkable, because the language of negative temperature, the idea of the inverted population, the framework of Boltzmann distributions and bounded energy spectra, all of it was being quietly, practically applied to working devices for generations before the potassium-39 gas ever cooled into its optical lattice. The theoretical ground had been prepared even earlier than that. Back in the 1950s, in the years when physicists were first building masers, the microwave frequency ancestors of the laser, Charles Townes and Arthur Schawlow, were working with exactly this framework. The maser, like the laser that followed it, relied on population inversion. And the physicists of that era used the language of negative temperature quite naturally when discussing amplifying media. The idea was not foreign or alarming, it was a descriptor. A way of saying more atoms are up than down, and the Boltzmann distribution runs the other way, and if you give this a temperature, it's a negative one. From that era onward, negative temperature has been a working concept in engineering. Not under that name, always. Engineers designing laser systems don't usually sit down and say, today we're going to drive our gain medium to negative temperature. They say, today we're going to achieve population inversion. But the two statements are the same statement. The physics does not care what word you use. And now here is the part that is almost too neat, the detail that makes the whole story fold back on itself. The optical lattice that Schneider and Bloch used to create the 2013 negative temperature gas, the egg carton of energy wells that gave the potassium atoms their bounded energy spectrum. The ceiling that made the inversion of motional energy possible, that lattice was made of laser beams. Interfering laser beams, carefully arranged, precisely tuned laser beams, whose standing wave patterns of constructive and destructive interference created the periodic potential that trapped the atoms and capped their kinetic energy from above. Without those laser beams, there is no optical lattice. Without the optical lattice, there is no upper bound on the motional energy. Without the upper bound, there is no negative temperature. The laser, which already operates on population inversion, which already embodies negative temperature in its gain medium, is the tool that was used to create negative temperature in a completely different physical system through a completely different mechanism. The effect creates the tool that creates the effect. The Ouroboros, the thing that loops back and eats its own tail. You could not make the negative temperature gas without the laser, and the laser, all along, has been running on the same principle that defines the negative temperature gas. There is something deeply satisfying about this, something that feels like a story told correctly. The universe's habits are consistent. It tends to use the same mathematics in different places, the same structures at different scales, the same mechanisms in different forms. Population inversion is one of those patterns. It shows up in nuclear spins in 1951, in laser gain media throughout the following decades, in ultra-cold atomic gases in 2013. The names change. The scales are wildly different. The physics is the same. Now, before we let all of that settle, because there is a little more to say about why any of it matters, and there is something honest we need to acknowledge about the word temperature itself, let me ask you how you're doing. Wherever you are tonight, however the hour sits around you, I hope you're comfortable. I hope the weight of the blanket or the softness of wherever you're lying is doing its slow work. This next part is the last stretch. We're nearly there, at the end of the strange and rather beautiful road we started walking together. So let's talk about what all of this might actually be for, beyond the astonishing experiment in a basement category of things. The first possibility is the one Schneider himself pointed toward in 2013. It has to do with why attractive interactions are normally catastrophic for a quantum gas. When atoms attract each other strongly, they pull toward each other. A cloud of atoms with attractive interactions doesn't just sit there, it collapses inward, or it goes unstable, or it implodes. This is generally bad if what you want is a stable gas you can measure and study. But in the 2013 experiment, the negative temperature state did something striking. It stabilized. The gas with attractive interactions in the inverted distribution in the negative temperature regime was mechanically stable. It didn't collapse. It sat there for those hundreds of milliseconds, holding its unusual configuration. And Schneider noted that a gas with attractive interactions in a negative temperature state produces something that behaves like negative pressure, a pressure that resists expansion in the usual sense, that has an unusual response to volume changes. And a system with negative pressure, he pointed out, is in some ways reminiscent of the cosmological puzzle that has been sitting at the heart of modern physics for decades. The universe, as best we understand it, is not just expanding, it is accelerating as it expands. Something is pushing it apart and pushing harder over time, and we don't know what that something is. We call it dark energy, which is a name for an unknown rather than a description of a known thing. And dark energy behaves in the equations like a medium with negative pressure. A medium that resists the way ordinary matter pushes back against compression. A medium that, in some of the frameworks we use to describe it, has an effective negative temperature in a certain thermodynamic sense. Schneider was careful. He didn't say the potassium-39 gas was dark energy. He said it was an analog, a system in the laboratory that shares some of the mathematical structure of the cosmological problem. A way to test, in a controlled setting, the behavior of systems that have properties resembling those of the thing we can't yet study directly. That is how physics often works. You make a small, controllable system that obeys the same equations as a large, inaccessible one, and you learn something from the small system that you can carry back to the large one. The 2013 gas, fragile and brief as it was, might be one of those small systems, a handle on something vast. The second possibility is thermodynamic, and it is strange enough that it deserves to be stated clearly, even though it needs an equally clear disclaimer. A heat engine, a device that converts a temperature difference into work, can, in principle, be made dramatically more efficient if one of its reservoirs is at a negative temperature. You remember the Carnot efficiency, the maximum fraction of heat that an engine can convert to work, is given by a formula that depends on the temperatures of the hot and cold reservoirs. For ordinary positive temperatures, this fraction is always less than 1. There is always some heat that must flow to the cold reservoir. You can never turn it all into work. But if you replace the hot reservoir with a negative temperature reservoir, something hotter than infinitely hot, the arithmetic changes. The efficiency can, in principle, exceed 1. The engine can, in principle, do more work than the heat it draws from the hot reservoir. This sounds like a perpetual motion machine. It sounds like the dream of free energy, of something from nothing. But it isn't, because it doesn't violate energy conservation. What it means is that work is being extracted from both the hot reservoir and the negative temperature reservoir. The energy is coming from somewhere, it's just that the temperature formula reassigns where. The negative temperature state is expensive to create. It takes energy to pump the population into the inverted configuration. You don't get something for nothing. You get something for something, and the accounting is more favorable in a way that engineers and thermodynamicists have thought carefully about, and will continue to think carefully about, as negative temperature physics becomes more controllable. It is a theoretical consequence, not a practical shortcut. But it is a real one, and it suggests that the thermodynamic frameworks we use to design engines and refrigerators and heat pumps might eventually have to accommodate a broader class of systems than they were built for. Now, the honest part. Because we have been careful throughout this night to follow the physics where it actually goes, and not where it would be more dramatic or comfortable to send it. There is something we need to sit with. In 2014, a paper appeared in Nature Physics. The authors were Junian Dunkel and Stefan Hilbert, and their argument was careful and serious and hard to dismiss. What they said, in essence, was this: negative absolute temperatures may not be real. They may be an artifact of how we define entropy. Here is what they meant. When we say temperature is the slope of entropy versus energy, 1 over T equals the change in entropy per unit change in energy, we are using a particular definition of entropy. The one due to Ludwig Boltzmann, the one that counts the number of microstates at a given energy, the number of ways the system can be arranged with exactly that much energy. It's sometimes called the surface entropy, or the microcanonical entropy of that energy shell. But there is another definition associated with Josiah Willard Gibbs. The Gibbs entropy, sometimes called the volume entropy, counts not the number of states at a given energy, but the total number of states up to that energy. All of them accumulated, and for classical systems at thermal equilibrium, these two definitions give the same temperature. They agree. For small quantum systems, or systems with unusual energy spectra like the ones we've been discussing, they sometimes disagree. And Dunkel and Hilbert's argument was that the Gibbs definition is the more consistent one, the one that satisfies more of the foundational requirements of thermodynamics without contradiction. And under the Gibbs definition, you never get negative temperatures. The 2013 gas would instead have a very large, very positive temperature. Extremely hot by the normal accounting, but still positive. Their paper was not a dismissal of the experiment. They were not saying the gas didn't exist, or that the measurement was wrong, or that the potassium atoms weren't in an inverted distribution. They agreed about all of that. What they were saying was, whether we call that configuration a negative temperature depends on which entropy formula we use, and they argued their formula was the better one. This was not received quietly. Rebuttals came. Dan Frenkel and Patrick Warren, Robert Swenson and Jiansheng Wang, and Schneider's own group among others, all published responses defending the Boltzmann entropy, defending the legitimacy of negative temperature, and arguing that the Gibbs definition has its own problems in other contexts, that it fails certain tests that the Boltzmann definition passes, that it is not as universally consistent as Dunkel and Hilbert claimed. The debate continues. It has not been resolved, not cleanly. There is genuine, ongoing disagreement among serious physicists over which definition of entropy is the right one for systems like these, and therefore over whether the phrase negative absolute temperature is meaningful or whether it is a convenient shorthand for a phenomenon better described some other way. This is important to sit with, because it is easy to hear a story like this. The flipped gas, the hotter than infinity, the wraparound temperature scale, and think that physics has handed us something clean and certain, something boxed and labelled and finished. But it hasn't, quite. The experiment is real. The physics of what the gas was doing is not in dispute. The atoms were inverted. The heat would have flowed out of them and into anything you touched them to. All of that is solid. What is not settled is the word. Temperature, whether that word, in its precise thermodynamic sense, applies to this configuration of atoms in this way, whether the axis we call the temperature axis wraps around through infinity and comes out negative on the other side, or whether a different, equally valid set of definitions gives you a large positive number and no wraparound at all. Dunkel and Hilbert made a real argument. The rebuttals were also real arguments. The question of which entropy definition is the correct foundational choice for quantum systems with bounded spectra is a genuine open problem in the foundations of statistical mechanics. And it is the kind of problem that looks dry and definitional from the outside and turns out, when you look closely, to be a deep question about what temperature even means. We said early on, didn't we, that temperature was not what we thought it was. Not the speed of molecules, not the familiar thing, the slope of entropy versus energy. And now we find that even that more careful definition has a crack in it, not because it's wrong, exactly, but because entropy turns out to be a word with more than one precise meaning. And the choice of meaning changes the answer to the question we thought we had settled. Physics does this. It gives you a satisfying answer, and then the satisfying answer turns out to rest on a question that wasn't asked carefully enough. And the new, more careful question opens into something more interesting than the first one. That is not a failure. That is the texture of actual knowledge. There is also something worth naming about the language that spread in 2013. The headline that went around the world, "Scientists create gas below absolute zero," was understandable. It was technically defensible. in the sense that on the temperature axis, with the Boltzmann entropy, the number is on the negative side of zero, and the scale is called the absolute scale. But below absolute zero is almost designed to be misread. It sounds like colder. It sounds like something colder than the coldest. And that, as we have spent time understanding, is exactly the opposite of the truth. The 2013 gas was not colder than anything, it was hotter than everything. Hotter than any positive temperature system in the universe. The Boomerang Nebula, a planetary nebula about 5,000 light-years away, the coldest known natural place in the universe, sitting at around 1 Kelvin, 1 degree above absolute zero, is a billion times hotter than the Munich gas in ordinary terms. And yet, in the wraparound ordering of the temperature scale, even the Boomerang Nebula, even the deep silence of interstellar space at 1 Kelvin sits below the potassium-39 gas in terms of what we mean by hot. The billionth of a degree gas outranks the 1 Kelvin nebula, not because it's closer to absolute zero, because it's on the other side of infinity. That is the paradox, and it is not a trick. It is what happens when you take the definition seriously, when you follow the mathematics all the way through instead of stopping when it gets uncomfortable. The temperature axis is not a line from cold to hot with zero in the middle and infinity at the far end. It is a circle. Or better, it is a line that wraps. Positive temperatures start at zero, absolute zero, the floor, the coldest, and rise toward positive infinity. But positive infinity and negative infinity are the same point on this axis. The same temperature. Infinite temperature. After that point, coming back the other way, sit the negative temperatures. They descend from negative infinity, which is the same as positive infinity, which is the hottest you can reach with a positive temperature, down toward negative zero. And negative zero is the hottest state of all, more ordered than anything. Every atom in the highest energy state, a complete, total, maximum energy inversion. The coldness variable, the inverse of temperature, is the one that runs smoothly. Equals 1 over T. When T is large and positive, is small and positive. When T goes to positive infinity, goes to zero. When T crosses through infinity and comes out negative, goes negative continuously, with no jump, no discontinuity. The strangeness is entirely in the choice to label things with T rather than. With coldness, the scale runs monotonically from plus infinity, which is absolute zero, down through zero, which is infinite temperature, down to minus infinity, which is the hottest state. No wraparound, no paradox, just a smooth, continuous axis from one extreme to the other. The paradox is the label, the physics underneath is clean, and here we are, you and I, at the end of the road. The long, careful road. We started, tonight, with a simple image, 100,000 potassium atoms, chilled to about a billionth of a degree above absolute zero, held in a lattice of light, and the claim that this cold-looking, fragile, barely there object, was somehow the hottest thing thermodynamics had ever described. Hotter than any star. Hotter than any plasma. Hotter than the most violent and energetic events in the observable universe. It sounded like a sleight of hand, like the kind of thing that physics sometimes does when it's feeling clever and wants to confuse people who ask sincere questions. But it wasn't a trick. Temperature is not about how fast things move. Temperature is about how a system's entropy responds to energy. How many new arrangements open up, how many new ways the energy can be distributed. When you pour a little more energy in normal matter, more energy always means more arrangements. The curve goes up. The slope is positive. The temperature is positive. This is so universal in everyday experience that we forget it's not a definition, it's a consequence of the fact that ordinary matter has no ceiling on its energy. Give matter a ceiling, and the game changes. Pin the top of the energy spectrum so that it's finite, so that there's a highest state the atoms can reach, and suddenly you can fill up the top and have nowhere left to go. Add energy when the high states are already crowded, and you don't open new arrangements, you actually close some off. You reduce the entropy. The slope of the entropy versus energy curve turns negative. And then the temperature, which is the inverse of that slope, is also negative. A negative temperature. On the far side of infinity. Hotter than everything positive, cooled into its strange stability by a magnetic field and a lattice of laser light. The history moved in patient steps to get there. Lars Onsager in 1949, thinking about bounded statistical systems, saw that the mathematics allowed it. Edward Purcell and Robert Pound in 1951, in their lithium fluoride crystal, held it in their hands, briefly for a few seconds, in the nuclear spin of a solid. Norman Ramsey in 1956 put the whole framework in its proper place, established the thermodynamic ordering, showed it was not an anomaly but a consequence of the correct definitions. And then the decades of lasers. All those lasers, all those gain media in population inversion, all those devices running, day after day, on the same inverted Boltzmann distribution, the same negative temperature physics, without ever needing to call it that. The maser work of Townes and Scholler, the laser revolution that followed, the fiber optic cables laid across ocean floors, the barcode readers, the laser pointers and disc players and medical imagers, a whole technology built on population inversion, on the upside-down distribution, on the mathematical reality of a gain medium that is, in the strict sense, at a negative absolute temperature. And then Munich in 2013, the optical lattice. The Feshbach resonance, the switch thrown simultaneously, flipping both the trapping potential and the interaction sign, pushing the potassium-39 gas from the coldest corner of its energy band to the highest, holding it there for hundreds of milliseconds, long enough to see what it did, to verify the inversion, to confirm that yes, heat would flow from this gas into anything positive, and that by every thermodynamic test we know how to apply, the system was in a negative temperature state, built from laser light, creating, with laser light, the physics that laser light already embodies. The story bends back on itself, as the best stories do. And yes, the debate about which entropy is the right entropy, the Boltzmann surface entropy or the Gibbs volume entropy, that debate is still running. Dunkel and Hilbert asked a real question. The rebuttals gave real answers. Neither side has fully convinced the other. The word temperature is genuinely contested in its application to these systems. The physics is not contested. The labeling is, and that distinction between a settled experimental result and an unsettled definitional argument is itself something worth carrying. It is the kind of distinction that matters everywhere in careful thought, not only in physics. But wherever you come down on the entropy argument, whatever framework you find most convincing, this much holds: there is a regime of matter in which the usual intuitions about heat and cold invert, in which adding energy decreases the disorder of the system, in which heat flows from the less energetic-looking object to the more energetic-looking one, in which the familiar temperature scale turns back on itself and something on the negative side of the number line is, in every measurable sense, the hottest thing around. That regime is real. It is demonstrated. It was demonstrated in nuclear spins in 1951, in laser gain media through the following decades, in emotional quantum gas in 2013. It is sitting right now inside devices you own, producing the light that scans your groceries, or plays your music, or connects your phone to the world. The strange is not elsewhere. It is here. It was always here. You didn't need to go to a Munich laboratory at a billionth of a degree above absolute zero to find it. You just needed to know where to look, and now you do. Wherever you are tonight, whatever corner of the world is dark around you, whatever hour is pressing quietly on the window, you have spent this time with one of the more beautiful paradoxes that physics has managed to uncover. Not beautiful because it is clean and simple. Beautiful because it is exactly the opposite. It is the kind of discovery that, once you've worked through it properly, makes the world feel more surprising and more coherent at the same time. More surprising because temperature does something most of us never suspected it could do. More coherent because the same mathematics keeps appearing in spins, in lasers, in ultra-cold gases, in places separated by decades and by the full span of experimental physics. The universe, it turns out, has a hotter than hot, an upside down, a far side of infinity that you can reach, if the energy has a ceiling, if the interactions cooperate, if the laser beams are aligned with enough care. And the ceiling is the key, isn't it? That is the thing that stays with me, the detail I keep returning to. It is the limit that makes the limitless possible. Ordinary matter has no ceiling, so ordinary matter can never be negative temperature. But put a ceiling on it, give it a top, an energy it cannot exceed, and suddenly the direction of entropy reverses, and the whole meaning of hot flips around. The constraint is what opens the new territory. There is something almost philosophical in that. Something that feels larger than the physics. But I'll leave that for you to find your own way into in the quiet that follows. The Boomerang Nebula is sitting out there tonight, 5,000 light-years away, at about 1 Kelvin. The coldest natural place we know. Immense, ancient, silent, in a way that makes silence here seem like noise. And a laboratory gas that lasted a fraction of a second, made of 100,000 atoms in a room in Munich, thermodynamically outranked it. Outranked every star, every nebula, every natural object we can point a telescope at. That is the world. And you are in it. You who are made of atoms that are right now in normal warm biological thermal equilibrium, electrons in their ground states, energy distributed in the ordinary way, entropy ticking along in the usual direction. You whose body temperature is somewhere around 310 Kelvin, which on the wraparound scale is so far from negative temperature that it might as well be absolute zero in comparison. And yet you spent this time understanding it. Following the argument all the way through, the slope of the entropy curve, the bounded spectrum, the Feshbach switch, the optical lattice made of laser light. You understood it, and if anyone asks you now what it means to be hotter than infinitely hot, you can tell them. Not as a slogan, as a thing you actually followed to its end. Temperature is the inverse slope of entropy versus energy. When that slope reverses, when the system has a ceiling and the high states are more populated than the low ones, the temperature crosses through infinity and comes out negative. And negative is not colder. Negative is hotter. The hottest possible. Heat flows from it into everything, the way heat always flows from hot to cold, except that now the hot side is wearing a minus sign. Below absolute zero is what the headlines said. But what they meant, what the physics means, is above infinite. on the far side of hot, in the place you can only reach by passing through infinity if you have a ceiling and a magnetic field and a lattice made of light. That is the answer. That is all of it. And it is a good thing to carry into sleep. Not a worrying thing, not an urgent thing, just a quiet, astonishing fact about the shape of the world. The kind of fact that makes the universe seem a little larger and a little stranger and somehow a little more hospitable. Because a universe in which the rules can fold back on themselves, in which the meaning of hot can invert, in which the same mathematics hides in a laser pointer and in a fleeting gas of potassium atoms, that universe is one that clearly has more in it than we first supposed. More corners, more surprises, more structure behind the familiar surface of things, and that seems, somehow, like a comfortable place to rest. If you've been enjoying these slow journeys through physics and the deep strangeness of the world, a gentle like and a subscribe to the Curious Voyager would mean a great deal. Small creators like me really do rely on your support to keep these going. And wherever you're listening from tonight, whatever time it is in your corner of the world, I'd love to know. Leave it in the comments when you wake. Sleep well, fellow Voyager. The next journey keeps until you wake.